All right, what's up, guys? So, virtual lab tonight. Here's how this thing is going to work. In fact, actually, this is technically not virtual. This is actually fully online because I'm pre-recording the lab itself and telling you guys what to do, and then you're doing the work on your own without interaction with me. But we'll go ahead and just roll with it. So tonight I figure I'd give you guys the opportunity to work on this on your own. I'm going to give you a couple of days basically to verify what we're going to measure as far as the voltage across two problems here of R3 for the first problem and R3 of the second problem utilizing loop analysis. Now, we all remember that loop analysis is an application of KVL in order to find unknown loop currents. But in this case, with two problems, we got 3 loops right here, and then we have 4 loops on the second problem. And so we all know that the voltage across R3 here could either be written of one of two ways, in which VR3, if we're actually referencing loop 2, is simply going to be equal to R3 times I2 minus I3. And so what you guys are going to do is go through and with loop analysis, utilizing the systematic process, find the values for I1, I2, and I3. You're going to develop your system equations, put those into a matrix. You're going to row reduce them, put them into echelon form, and then take the values for I2 and I3, and then simply multiply that by the resistance of R3, and that will give you the voltage, and in this orientation, positive to negative, which is why I say we reference loop 2. So for the second one, what we're going to do is also find that voltage across R3 reference to I1 because I have a positive to negative orientation in this manner. And so for here, you guys will do the same thing. You're going to write out your 4 system equations. You're going to solve those system equations with the augmented matrix, put it into row reduced echelon form, and take the values for I1 and I2. And so in this case, VR3 is going to be equal to R3 times I1 minus I2. And so these calculated values for the voltage across R3, in both cases, what we're going to do now is I actually have both of these already hooked up. And we're going to basically put power to them. And once we put power to them, we're actually going to give you a measured value for the voltage across R3 in the second problem, and in the first problem, the voltage across R3 for here. So I'm going to give you guys those measured values, and then you guys are actually going to do the calculations and verify that those measurements actually come out to be correct. And if the voltages across both resistors come out to be what you calculated, then that proves that the method of loop analysis of finding unknown loop currents and then applying them with basically the form of R3 times I2 minus I3, or in the second case, R3 times I1 minus I2, it proves that the method actually is valid and that it actually works. So let's take a look at this, the actual boards that I've got set up for you guys. So we're going to look at the first one, and then we're going to put power to it. We're going to verify that the board is actually the connected circuit that should be representative of this schematic here. So we're going to verify that, we're going to hook it up and see what value for the voltage across R3 is, and then we're going to do the same thing for number 2. All right, hang on just a second. All right, working off these little cameras can be a little bit difficult here. So let's see if I can angle this down appropriately. And hopefully this thing will not fall. And I'm afraid it's going to. Okay, so that is absolutely the best I'm going to be able to do right now with these setups. But let's take a look at the very, very first one here. So this is what we have for the first problem, so simple 3-loop problem. Let's take a look at the board here and verify that this is actually the connection of this schematic here. So one thing to note, I forgot to say this up front, is that I'm sending you guys these values for the resistors attached in the email. So that's what you guys are going to use. So if we look right here, sure enough, our 10 volt source is going to be connected between these 2 points here. Here we got R4, here we got R5, R3, R2, and R1, in which we have a singular upper loop at the top. And then down here we have that second loop that involves those 3 resistors and that are connected with a common point of connection down here. So I'm going to put 10 volts to this sucker right here, and I'm going to measure the value of the voltage across R3, which is this 100 ohm resistor. All right, so let me get this set up real quick, and then we'll get a measured value, guys. All right, gotta verify, in fact, actually, that this source is producing 10 volts. So I'm gonna turn on. All right, so I got 11, so ooh, no, we need to crank that down. 10 volts. And as we can see right here, guys, sure enough, hopefully you guys can see that. The wonders of all this stuff, right? Sure enough, we got 10 volts right there. Cool, 10 volts. So now I'm actually going to take this guy and I'm going to measure the voltage across R3. Maybe I should have test run this. I apologize. So, taking the measurement across R3, for here we actually get 0.64 volts. And so when you guys go through and actually make your calculation, with the first one that would be R3 times I2 minus I3, the voltage should come out to be equal to 0.64 volts. So that's what I want you guys to verify with your calculations. All right, so I'm going to put this guy on standby. Let's prove that I've put it on standby for safety measures. Oh, yep, negative 0.064 millivolts. So let's switch this guy out. Just going to maneuver this one to the side. And now we're going to take number 2 and we're going to find the voltage across R3. In this case, it's a 208 resistor. And like I said, I'm sending you guys these values in the email that will have the video, this video attached, as well as the document here. So let's verify that this, once again, matches this schematic here. So as the schematic shows, we have 10 volts and then we have 4 loops. And sure enough, 10 volts is going to be connected in between right here, positive to negative. Here's our first loop, our second loop. This will be our third and then our fourth. And we can kind of see here that where R5 and R6 are connected, there's nothing in between these 2 points. So we just put a piece of wire, just as we've done before. All right, let's put some power to this thing and see what we get for our voltage. All right, so let's verify. All right, DC power is on. And let's verify that we got 10 volts there. Sure enough, we do. So now I'm going to measure across R3. And the voltage across R3 is in fact actually 3.09 or 3.1 volts. So when you guys do your calculations with R3 times I1 minus I2, that should give you that value of your voltage, 3.1 volts. All right, and guys, that's it. So all I want you guys to do is go through and do your calculations with these values I've sent in the email, and then just compare those to what I have measured on both of these boards. And so send me your calculations, show me your simultaneous equations, how you put it into matrices form, and what values you got for all the currents, and then how you actually calculate the voltage across R3 for both problems. Very, very simple, should give you guys some good experience, but again, by measuring the voltage across those resistors and then comparing that with the calculated voltage utilizing the loop current values that we got from the system equations, that will prove that this method does in fact work just fine. All right, so lab after this one, we will do this one in class, and we will do it for source transformation. We're going to see some cool stuff happen then. So I'll see you guys next week on this one. Take care.